Today we're going to be going over some things from chapter 3. I do not expect to get through all of these problems today because it's page 7 to the end. I'm going to skip some. Some of them are just kind of redundant, like we don't need to do 14 mole conversions. We just need to do a couple of them. You get the gist, okay? And next class, after our lab should not take the entire block. So we'll have some time after the lab to do a few more problems. Okay, so you should be on page 7 in your packet. So on page 7, we have this average sum of mass calculation. We're just going to run through it. But as it was pointed out to me yesterday during third block, I've been doing this problem for 5 years, and we never realized that the percent abundances add up to more than 100. And they should only add to 100. So let's correct them, and then we'll do the problem. So really, this first one should be 90.48. Like all of them are wrong for some reason. Second one should be 0.27. And the third one should be 9.25. All right. So when calculating average atomic mass, how do we do that? Well, yes, we should use a calculator, most likely.
We multiply each percentage by the relative mass and add them all up.
Yep, we multiply the percent abundance by the relative mass and add them all up. At no point are you going to divide by how many there are. Taking like 3 numbers, adding them up and dividing by the number that you have, that's just a straight average. This is a weighted average. Okay? When we multiply the relative mass by the percent abundance, what do we need to do to the percent abundance? Convert it back to a decimal. So divide it by 100 or just move the decimal to the left. So, for example, we take 19.992 times 0.9048 plus 20.994 times 0.27. Oh, sorry, forgot to move the decimal. 0.0027 plus 21.991 times 0.0925. And add them all up. Now, for sig figs, I'm going to tell you guys a little secret. When it comes to average atomic mass, I hate worrying about sig figs. It's always a pain for average atomic mass. I'm a stickler about sig figs for everything else though. Okay? Now, honestly, with average atomic mass, the percent abundances, we can assume that those come from counting numbers. So therefore, we can ignore the sig figs from the percent abundances. So really, just use your sig figs based off of your relative masses. So your answer should keep it to 5 sig figs, 3 decimal places. Okay. So when you do, go ahead and do all of that math. And what do you get? 20.180, because it's 1796 and the 6 rounds the 9 up, which rounds the 7 up. All right, what's our unit? AMU. If you got a little bit slightly off of that, you might have just typed a number wrong earlier on. Maybe you did 922 instead of 992 in the first relative mass or something. But you understand the process, right? Cool. This isn't going to be a huge topic on AP, on the AP exam. There might be like a multiple choice question about this. Or it might be like part of a pre-response. It's not a huge topic, but you still need to know how to do it. All right. Now let's go into some mole conversions. Mole conversions are a tool, as is stoichiometry. It's a tool to help us get to something else. So you should know how to do these mole conversions. You should know how to do stoichiometry. We'll do a couple of these. So we'll start with A. or with 11A, number 1 up here. So how many molecules are in 198.5 grams of sodium chloride? Okay. So what are we going to start with? 198.5 grams. What's sodium chloride's formula? NaCl. What are we going to convert that to first? Moles. When in doubt, go to moles, and that's always kind of what you should be aiming for, because once you're at moles, you can get pretty much anywhere. So in order to convert this to moles, what information do we need? The molar mass. And how do you find the molar mass of sodium chloride? You use the periodic table, which I haven't put back up on the wall yet. You use the periodic table, and what do you get as sodium chloride's molar mass? 58.44. Good. And then we're at moles, so we can go to molecules. How many molecules are in a mole? Avogadro's number, 6.02 times 10 to the 23rd. If you use 6.022 times 10 to the 23rd, that's perfectly acceptable. That's actually the one that's on your formula sheet. But yeah, it's on your formula sheet if you ever forget Avogadro's number, which you shouldn't because you had to memorize it when you took first year chemistry. Okay. Now, technically, these are not molecules. Molecules refer to the particle of a covalent compound. Sodium chloride is ionic. So technically these should say formula units, because that's what the particle of an ionic compound is called, but semantics, right? All right, but same process. So go ahead and calculate that. How many sig figs are we going to have? 4, because you go based off of your given. Whatever you start with, that should be the number of sig figs at the end. Molar masses and Avogadro's number, those types of things are considered to be constants. We ignore their sig figs. Okay. So what is our answer with proper sig figs?
2.045.
10 to the what? 24th. Molecules. NaCl. Good. Always clearly put a unit and a label. Make it really clear what you solved. And also get in the habit, if you're not already, of like maybe boxing or circling your final answer. That's really great on the AP Chem exam on the free response section to make it clear what you finally solved. Oftentimes, and I think that the AP graders kind of do the same thing. If we grade these backwards, we look at your answer first, and then we look to see if that's right and that you have appropriate work. And if it's not right, we see where you went wrong. All right. We don't need to do number 2 because it's the same kind of thing. It's actually just working backwards. Let's go ahead and skip to this one, number 4, which is D on your page. How many atoms of chlorine are in 654.5 grams of calcium chloride? All right, so first of all, what is the formula for calcium chloride? CaCl2. Okay. So let's just start off. We have the mass of calcium chloride. So where do you think we need to go first? The moles. So 654.5 grams calcium chloride. Let's just go ahead and convert that to moles. So we're going to need the molar mass of that. Has anyone calculated it yet? What do you have as your mass for calcium? You did Ca2Cl, gotcha. It should be 110.98, right? Okay. And now that I'm at moles of calcium chloride, I want to get to atoms of chlorine eventually. So where can I go next?
For 1 mole of calcium chloride and 2 moles of chlorine.
So how did you know that there was 2 moles of chlorine?
You know, formula.
Because the formula. This isn't a reaction here. So we're looking in this calcium chloride ionic compound here, we have 2 chlorine atoms for every compound. So it's kind of like a stoichiometry mole ratio, but it's within its own compound. You may or may not have done problems like that in first year chem, but you can use mole ratios for a lot of things, okay? So for 1 mole of calcium chloride, we have 2 moles of chlorine atoms within that compound. Okay? And now that we're at moles of chlorine atoms, how do I get to number of chlorine atoms? Avogadro's number. Exactly. Because we know there are 6.02 times 10 to the 23rd atoms of chlorine for every 1 mole of chlorine. And then you can solve.
It's 7.101 times 10 to the 24th.
Yes, exactly. 7.101 times 10 to the 24th atoms of chlorine. Okay? Cool. All right, we're going to go ahead and skip to page 8. And there is a table in the middle of page 8. We're going to do one of those. We are going to solve, complete the chart for the unknown compound. Can I go to the next page? Are you good? All right. All right, so like I said, we're going to do this unknown compound. So given the things, and so we are going to need to find the molar mass of the compound. We're going to need to find the number of particles for that unknown substance. I say compound, but we don't know what it is. It could be just an element, it could be a molecule, whatever. We are given the moles of the sample and the mass of the sample. So we need to find molar mass and number of particles. Which one do we want to find first? It really doesn't matter. All right, let's find the molar mass first. So for the unknown, to calculate the molar mass, how do you think we're going to solve that? Yeah, but the units for molar mass are grams per mole. We have the grams, and we have the moles. The reason I'm pointing this out is because I have seen on previous free responses for AP chemistry, there has been a portion of a problem where you have to find the molar mass of the substance. And I don't know about the rest of the world, but for some reason, my students in the past, a lot of them get tripped up by it because it is so simple. You just take grams per mole, but they're like, wait, how do I find this? So I want to make sure that sometimes they are simple questions. Okay? So yeah, if you ever ask for grams, or if you're ever asked to find molar mass, look to see if you have the grams or you can find the grams. Look to see if you have the moles or you can find the moles, and then divide. Okay. So what is the molar mass of this unknown sample? 119? 119? Grams per mole. And we're just going to leave it at 3 sig figs because that's how many sig figs we have in our numbers that we're dividing. Typically, molar masses, when we pull them from the periodic table, we're going to go to 2 decimal places. But this, we're not looking at the periodic table, we're using other data. Okay. And then, so that's 119. And then to find the number of particles, what do we want to use? So we use Avogadro's number, and what are we converting? Yeah, just start with the moles and convert that to particles using Avogadro's number. And I'm putting particles because I don't know what type of substance this is. So I don't know if this is an atom, if it would be a molecule, or a formula unit. So I'm just saying particles. That's like the generic term for it. And what do you get? 2.87 times 10 to the 23rd? And that would go there. Okay? So, on your own, maybe how you study for your Unit 1 test, you can do more of these as practice. The answer key, the completed notes for all of this is already up on Vision. Okay. Go ahead and turn to page 9. Percent composition, I just have one problem of percent composition, just to run through, practice that. In general, how do we find percent of something? What? Yeah, part over the total, or part over whole, then what? Times 100. That's the general formula for any sort of percentage. When we are given a formula of a chemical compound, of the chemical, to find the percent composition, we use the molar masses. So the part would be the molar mass that is contributed from a particular element, and then the whole would be the entire molar mass of the compound. So let's go ahead and calculate the entire molar mass of nickel 2 phosphate. Remember, when you pull those numbers from the periodic table, round to 2 decimal places, your periodic table that I gave you on day 1 already is rounded to 2 decimal places, but if you're using another source, you might have to round.
365, 29, all 365, 366.
66.01.
That's what I have. Did you use the periodic table I gave you, or did you use another source?
I use none. That's exactly it. And periodic table. Apps periodic.
Okay, well, you got close enough. So 366.01 grams per mole. That's what I got based off of the AP Chemistry College Board periodic
That's what I
table.
got.
Oh. All right. So now you're going to find the percent of each element. So for nickel, what's going to be on the top?
176.07.
Right, 3 of the nickel atoms. Okay, because remember, you have to deal with what they contribute. So this is how I wrote it. I lost my page. There it is. So I just, that way I'm showing you that it's 3 times nickel's molar mass. And then phosphorus. How many phosphorus atoms are in that compound? 2. So 30.97 times 2 over 366.01. And how many oxygen atoms are there? 8. Good. Just want to make sure we all knew how to determine the number of atoms in a compound. So go ahead and calculate those percentages. And you can just go to 2 decimal places for your percentages. For percent composition, we don't really worry about 6 things that much. Has anyone found any of them yet? Yep, go ahead.
Nickel's 48.11%.
Nickel is 48.11%.
I combined the compound application.
Oh, you did it as PO4?
Yeah.
Gotcha. And now we're just waiting on oxygen. 34.97. Cool. And now all those percent compositions should add up to 100. It's okay if it's a little bit off, like if it's 100, you know, 100.01 or 99.98 or something like that. That's okay. Right? Cool. Empirical formulas. Empirical and molecular formulas. So, this is like working backwards from the percent compositions to the formula. It's not just the reverse steps though, because we don't know enough about the compound's formula. We don't know the entire molar mass, stuff like that. So there's a little saying, like a little poem to help you remember the order to do empirical formula. It's percent to mass, mass to moles, divide by small, multiply by whole. So, percent to mass. So whatever your percentages is, you just say that those are the grams. If we assume that we have 100 grams of this compound, then we would have 71.65 grams of chlorine and 24.27 grams of carbon and 4.07 grams of hydrogen. So you just make the percentages grams. Then you convert all of those grams to moles using the molar mass of those individual elements. Then, once you have the moles of everything, you're going to divide by the smallest number of moles, divide them all by the smallest. That gives us a ratio. And then, if necessary, multiply by whole, okay, to get them to whole numbers. So let's go through this. So chlorine, we have 71.65 grams of chlorine. We're going to convert that to moles. The molar mass of chlorine is 35.45. Let me set up the other two. 24.27 grams of carbon. Converted to moles, and then 4.07 grams of hydrogen. Convert that to moles. Okay. Now, a helpful hint, when you're calculating the moles of these things, carry like 4 decimal places. I know that doesn't make sense for sig figs, but actually carry out many more than you need. Because if you round off too early, it could mess up your ratios. You know, it could make your ratios not exact. It makes the division a little better if you just carry out several decimal places. So when you do these mole conversions for chlorine, you should get 2.0212. For carbon, you should get 2.0208. And for hydrogen, you should get 4.0297, or thereabouts. Okay? So now, what are we going to do? Divide by the smallest number of moles. Which one has the smallest number of moles? Carbon. So we're going to divide them all by 2.0208. Well, 2.0208 divided by 2.0208 is 1. Because anything divided by itself is 1. And even chlorine, that's really close to 1. It's just a little bit over 1, but we can round it down to 1. Okay. And then for hydrogen, what is that? 2. So it's practically 2 when you do the division. So since our ratio gave us all whole numbers, we don't have to do any multiplication. Makes it nice and easy, right? So what would be the empirical formula of this compound?
CH2Cl.
No, H2CCl. You have to go order of charting, right?
Typically, so this is an organic compound. Typically, carbon comes first,
Oh, it's
then
organic.
hydrogen. Yeah. So it would be CH2Cl, but if you wrote it in a different order, it's fine. You're not going to be penalized, at least not right now, not until we learn more about how things are written. Right now, it's fine. Okay, if you wrote it in a different order, as long as you're showing that there's one carbon, two hydrogens, and one chlorine. Okay, so that's the empirical formula. So we determine the empirical formula. It's also asking me to find the molecular formula of this compound. The molecular formula is the empirical formula is the lowest whole number ratio of the atoms in the compound. So it's like a covalent compound that's been reduced down, or an ionic compound that's completely reduced. A molecular formula shows you the exact number of atoms, like how many they actually have. Okay? It'll still be this ratio, but it might not be this simplified form. So to find the molecular formula, we're given the molar mass of the molecular formula. We have to find the molar mass of the empirical formula, and then divide and multiply through. So go ahead and calculate the molar mass of this empirical formula.
$49.476.
49 point,
476.
so 48.
Yeah.
So you should get 49.48. That's the molar mass of the empirical formula. We're going to divide that into the molecular formula's mass. So 98.96 divided by 49.48. What does that equal? 2. Which we then distribute through the empirical formula to get our molecular formula, which would be C2H4Cl2. Is this all coming back to you? It should be. Okay? Alrighty. Let's go ahead and skip the next problem. Let's go ahead and jump to page 10, number 14A. This one. All right, this one has asked us to balance that equation and draw a particulate diagram of the reactants and products. So take a moment to balance that equation. So what is this balanced?
1, 3, 1, 2, or 2, 3.
1, 3, 2.
Yeah, 2, 3. 1, 3. Come on.
1, 3, 2, 3.
Come on.
Okay, so now drawing a particulate diagram, how you draw it, remember it's kind of like a Lewis structure, but instead of using the symbols, you're just using circles to represent the different atoms. And you'll do different types of shading to show different atoms, okay? So the way I did it is, and for right now, you don't necessarily have to know the way that this C2H5OH is bonded together, so let me just show you. So I'm going to represent carbon with a large colored in circle. So I have 2 of those. And then on my first carbon atom, I have 3 of these hydrogen atoms. So I'm going to represent that with a small empty circle. And then on the next carbon, I have 2 of those hydrogen atoms. And there's also the oxygen atom on there. So I'm going to represent oxygen with a large open circle. And then there's also another hydrogen like that. Okay? With the particulate diagram, you don't necessarily have to include a key to then be like, this is carbon, this is oxygen, this is hydrogen. I'll know enough. I'll know sooner or later. Now for oxygen, I have 3 O2s. 3 O2s. What did I use to represent oxygen?
Big circle.
Big open circle, right? So how many of these am I going to draw? 3 of them. And it's going to be, yeah, diatomic. Yay. And now CO2, how many of those am I going to draw? Two. Remember, my carbon was my big colored in circle, so I'm just using the same symbols from before. You do not need to indicate that those are double bonds. That's the one thing about particulate diagrams is you don't actually have to show the bond. I don't know why, but AP College Board loves doing these particulate diagrams. A lot of times you'll either have to interpret them or draw them. Again, not like, it's not going to be the entire test, but there'll be one question where you have to draw something like this. And then we have our,
Dihydrogen monoxide.
yes, you have our DHMO, or water. Yes, which you can draw as Mickey Mouse, or you could draw the circles on the bottom if you really wanted to. Draw them on the side. Yeah, so your water molecules. Cool? All right, moving on. Let's go ahead and skip to page 11. We will do the problem at the top of page 11. All right, this one. So, an industrial method for the production of elemental zinc from its ore is to roast the crude ore in oxygen and then react it with carbon monoxide. The following reactions describe the chemical process. So, they're there. We have a 10 kilogram sample of an ore containing zinc sulfide that was chemically treated according to the reactions described above and producing 2.85 kilograms of zinc. Determine the percentage of zinc sulfide contained in the original sample of the ore. So this ore, this 10 kilogram sample, is not pure zinc sulfide. It's zinc sulfide and a bunch of other stuff that doesn't react when we roast it in the oxygen. Okay? Only the zinc sulfide is going to react when we roast it in the oxygen, and then we can figure out how much was in there originally. Okay? So, how do you think we're going to start this problem? Starting with which value? Because we have 2 kilogram values.
Divided the pure zinc.
Which would be?
2.85.
Thank you. That's what I was looking for. So we're going to start with this, the 2.85 kilograms of pure zinc. Because we can't even take the 10 kilograms to moles because we don't know what the chemical formula of the entire ore sample is. Because there's more than just zinc sulfide mixed in there. Okay? So we're going to start off with the 2.85 kilograms of zinc. So I want to take that to moles, right? Before I can take it to moles, what do I have to do with that? Convert to grams, because the numbers on the periodic table are grams per mole. How many grams are in a kilogram? 1,000. All right, so just an easy one-step mole conversion, or not mole conversion, unit conversion. Now we can go from grams to moles using the molar mass of zinc, which is 65.39. And now I'm at moles of zinc. Zinc is only in my second equation up here. So I'm going to take zinc, and now I'm at a mole-mole ratio step. So I'm going to go from zinc to what substance? Yep, go from zinc to zinc oxide. Okay? Because zinc oxide is a reactant of the second equation and a product of the first equation. So in this second equation, it's a 1-to-1 ratio of zinc to zinc oxide. And then I can go from zinc oxide to what? Zinc sulfide using the second equation. Because if I were actually to stop the problem now, I would know the moles of zinc oxide that were produced from the ore that was roasted in the first equation. So I can actually just make it all one big step. Here I have a 2-to-2 mole ratio, 2 mole to 2 mole ratio. Yeah? And then just one more step. I've run out of room, so I'm gonna write it down below. Once I have moles of zinc sulfide, where do I need to go next? Grams of zinc sulfide using the molar mass. Has anyone calculated that yet? 97.45 grams of zinc sulfide. So this will tell me how many grams of zinc sulfide were originally pulled from the ore. I want kilograms, right? So one last step, going back to kilograms. So what do you notice I did at the beginning and the end? What do you notice I did at the beginning and the end? They're opposites, right? So what can we do with that? Cancel it out. Don't even bother doing that calculation. Save yourself time. Because time is important. It's limited on these exams, as you've already experienced with these quizzes that we've had. So, go ahead and calculate that. You can also eliminate the 2/2 right here, because we know that's 1. So really, it's just 2.85 divided by 65.39 times 97.45. And that will give you the kilograms of zinc sulfide that were in the ore to begin with. And what do you get? 4.25? 4.25 kilograms of zinc sulfide that were in the ore to begin with. And now, I want to find the percent of zinc sulfide that was in that ore. So what do I do?
Divided by 10.
Divide that by 10. And then times 100. Which is 42.5%. So that's how much zinc sulfide was in that ore sample. That means that, you know, kind of like tells you the purity of that ore and stuff like that. Okay? We're going to do one more together for today. And that's one of the limiting and excess reactant problems. It's not the first one. Sorry. We're going to go ahead and skip to page 12. We're going to do the top one. This one. So, I know that not all of you had me in first year calc. The way I do limiting and excess reactant type problems might be a little bit different from how you do it. Okay? Let me show you how I do it, and then I'll stop this, and I'll explain some more stuff, okay? But let me at least show you how I do it. It might make things a little bit easier. It's where you find the limiting reactant first, and then you do stoichiometry. So it saves stoichiometry. So it reduces the amount of stoichiometry you have to do. Okay. So we are told that we have 50 grams of each reactant, both calcium and nitrogen, that are reacted together, and we want to know how much calcium nitride can be produced. So for this, we're going to take the 50 grams, take the amount of both reactants and convert them to moles. So we're just going to convert 50 grams of calcium to moles. And 50 grams of nitrogen to moles. Molar mass of calcium is 40.08. and nitrogen N2, you have to multiply 14.01 by 2, getting 28.02. So go ahead and calculate both of those moles. And what do you get for calcium? 1.25. And for nitrogen? 1.78 moles of nitrogen. All right, now we are going to divide the moles of each substance by their coefficient in the equation. So we're going to take the 1.25 moles of calcium and divide it by 3. And for nitrogen, divide it by 1. Obviously, this is going to stay as 1.78. But what is 1.25 divided by 3? 0.417. All right, whichever one gives the smaller answer, that was your limiting reactant. So which one's smaller?
Calcium.
Yep, calcium. 0.417 is smaller than 1.78. So therefore, calcium is my limiting reactant. Just to review, 3 dots in a triangular formation means therefore. You've probably seen that in geometry proofs. I use that shorthand a lot. Okay? So, calcium is our limiting reactant. So now we can do our stoichiometry. So we can take the moles of our limiting reactant and do stoichiometry with that. So 1.25 moles of calcium. We could go back to the mass, but the first step would be this, what we've already done. So why make yourself have to do more work, right? So 1.25 moles of calcium, and now we're just going to go from moles of calcium to moles of calcium nitride, and then to grams. So we're going to need the molar mass of Ca3N2. Anyone calculated that yet? Good, 148.26. And then salt.
61.7.
61.7? Okay. So that's I find that the easiest way to do limiting reactants. Let me stop this recording and continue talking to you guys.